Let's get started here. You have questions from homeworks, it sounds like. So let's start there. Anybody want to lead off on that? Happy to run through some examples or hit on some things that we had trouble with over the weekend. It's been a couple of days since we talked about 2.1 and 2.7 with the test, and then the test, talk about afterwards. So it's been a couple of class days. So if you're a little foggy on that, again, it's understandable. It's been some time. Adrian.
I feel like it would be helpful if you could go over the finding the f prime thing.
Yeah.
It was I think number 27 through 31. Any of those.
Perfect. Yeah, we can do that. Sure. And that was in 22.7, right?
Yeah.
Alrighty. So let's grab a couple of these. Does anybody, Adrian said anything from anything from this section. Does anyone have a specific one from here that they want to see? Aaron?
31.
31? Sure. And again, we can, if you're like, oh, I want to see a different one, we can, there's time for more than one. So start with our definition of a limit. So again, you could have used the other version. I like this one. I think it's usually the easier way to go. So far, so good. Okay. So f of a plus h just means that I'm going to be taking this a plus h and plugging it in to f, right? Pretty good with that? And then same idea with the a. So far, so good. I can simplify this out. I'm just distributing the 2 through. But if I look at this, there's no way for me to combine the like terms here. Eventually, I need to get it so there's only h's left, right? So if I tried plugging this 0 in for h right now, I'm just going to get 0 over 0, which we know is indeterminate. So we got to find some way to clear that indeterminate hurdle here. If I have radicals, and it's indeterminate, what's kind of our go-to method? Multiplying by a conjugate, right? So that's what I'm going to do here. Yeah, come on now. So do that. You feel okay? And we'll multiply this stuff out. Do we feel okay still? And what I simplified that down to, again, I didn't show the foiling in the top, but I feel like we've done this technique a bunch of times and we should be okay with like seeing the foil that happens, even if I'm not writing it out, right? I would hope you'd be able to go straight to the simplified form and not have to, you know, first outer or last it. Just have to be careful that you're getting everything squared that you need. So if I distribute this negative sign through, oh, it's like, uh-oh. So that's a minus sign there. These need to be minuses. Oops, daisies. Okay. Everybody okay? It's like, why isn't everything canceling out the way it's supposed to? That makes more sense. So after we do some reducing, I notice the only thing left in my numerator is this, right? So reduce our h's at the same shot. We all still on board? Adrian, you good? Mia, you good? Okay. So let's rewrite this now that we've simplified a bunch of this down. Good with everybody? So now I can do my direct substitution. Notice there's no way to get a 0 over 0 anymore because the numerator is a constant. So I know that I've cleared that hurdle. Notice I've dropped the limit now that I did the direct substitution. We hung on to the limit all the way up to that point. So I'm going to end up with negative 2 on top, and I have a root of 1 minus 2a plus another root of 1 minus 2a. It's like 2 roots of 1 minus 2a. And then, so there's my f prime, or the derivative of f of x at a, or the instantaneous rate of change of f at a, or the slope of the tangent line to f of x at a. This is the answer to all of those questions. They are all asking you to do the same thing. Depending on context, we may phrase it all sorts of different ways, but it's the same process regardless. Adrian, does that feel better? Yeah. Aaron, you're happy with what we did there? Multiplied by the conjugate, you just got like lost in algebra there someplace probably. It's easy to get turned around. I made the silly like drop my negative sign on there, and it's like, why isn't this working? And after years of experience, it's easy. You know, you guys are first timing this, so it's hard. Kate, how are you doing? Do you want to talk about another problem? Are you sure? Yeah. Okay. I'm happy to do more, guys. Or if there's stuff that like you saw in the homework that you're just like, I just don't know what to do with this, or you know, like now's the time to talk about it. Aaron.
No, we do number 8 and 2.7.
2.7, number 8. Yeah, we'll get both of those, and then we'll see where we're at and maybe move on to the new stuff. Does that sound like a plan? So number 8. Okay. and then we'll go to 22. Me, if I start trying to move on without coming back to 22, you need to stop me and be like, hey, you promised. Okay. Hold me to that, because, you know, like, I don't know, I forget and stuff. Stuff happens. All right. And this is 8 that we wanted to look at, Aaron?
Yeah.
Yeah, okay. And this is the right problem?
Mm-hmm.
Okay. So it wants the equation for the tangent line. For this, we need point, which we got, and the slope, which we're going to get from the derivative. Ready to go to the plan? So that slope is going to be the derivative of, it's going to be the derivative of y at x equals 1. Basically, go with the plan. So use my definition. You're okay with the notation that I'm using here? Or I'm just calling it y prime instead of, like it was f of x, we'll just call it y prime of x. So everybody's okay? Marcelino?
You still call it y prime with the equation?
So when we do the subs, oh yeah, of course not. No. Yes, thank you. Yeah, for sure not. Definitely, yes. Very good. All right, ready? Let's roll. So again, all we're going to be doing is plugging in. So when I plug in the 1 plus h in for x, and then what's y of 1? Just 1, right? So this is y of 1 over here. You could plug it through, but like save yourself the aggravation. Is everybody good with how I've gotten to here? The plugging in that I did? It's just kind of like a function composition kind of feel to it, right? When you guys did function composition in Algebra 2 and Pre-Calc, very much feels the same way. So let's clean this up a little bit. So that's going to be 3 plus 2h over 3 plus h. I still have the minus 1 up here, and over h. So if I look and I try to do a direct substitution here, I end up with 0 over 0, right? So I know there's an indeterminate form going on that I have to clear that hurdle on. Probably the best way of going about this with the complex fraction is just try to simplify that complex fraction. The easiest way to simplify a complex fraction is just to multiply by the least common multiple of the denominators. So there's really only one denominator here that matters. It's just the 3 plus h, because the other denominators are just 1s. So I'm going to multiply the top and bottom of this by 3 plus h. So when I multiply to here, 3 plus h's cancel and they're gone. When I multiply to here, well, I just have negative of 3 plus h. And then never multiply the denominator out, because hopefully I'm going to do some reducing and it needs to be in factor form to do that. So typically I'll never multiply the denominator out unless I have like a good reason to do so, like if I have two things being added or something down there. I can do that. So if I distribute the negative through, that top is really negative 3 minus h. Still good? So 3 plus 2h minus, well, let's just do the subtraction, right? So those guys go, this guy goes, and that's gone, so I'm just left with h on top. So I have that. So far so good. And then h is reduced, and we'll do our direct substitution. So our slope is 1/3. So if I write the equation for my tangent line, y minus y of 1 equals m times x minus 1. And that's good enough. If you wanted to, you can, I don't know how the back of the book's answer was, slope intercept form or how they formatted it, but this is correct. You know, I would accept this on a problem direction, say, write the equation for the tangent line. It's an equation for a line, it doesn't have to be prettier than that. It's standard form or slope intercept form or point slope form. It doesn't matter to me if the directions aren't specifically asking for, you know, like show it's, you know, and then write your answer in this form, or show that the tangent line to this curve at this point is, you know, and then blank, and then like you gotta get to blank, but I think this is good enough. Does that feel okay, Aaron? So again, probably the hardest part there was getting the limit correct, right? Clearing that indeterminate form and getting to the simplified down to 1/3, and after that it's, you know, it's not bad. Mia, you're on 22. Okay, let's do that. And this next section should be good for you guys if you're still like, feel like you're kind of getting your bearings on this, because it's not a lot different than what we've just done. So that's good. That's not where that was supposed to land at all, but whatever. Okay. All right. So it says sketch the graph of a function g for which all these criteria are met, right? That's like a bunch of stuff. Quick start, how many possible answers is this going to have? Like infinitely many, right? All your graph has to do is hit the criteria, but it could look wildly different depending on like how you draw or connect the parts here that we're given, right? Everybody okay with that to start? So I'm going to draw an answer. Obviously, answers can vary here, but to some extent, they'll all kind of look similar. All right. So it says g of 0, g of 2, and g of 4 are all 0. Oh. Why did it erase? G of 0, g of 2, and g of 4 are all x-intercepts, right? Everybody feel good there? Okay. It says g prime of 1 and g prime of 3 are 0. Remember, g prime is like the slope of the tangent line to it. So, are we given anything in between? G of 0 is 1, okay? Or g prime of 0 is 1 and g prime of 4 is 1. So I'm just going to kind of sketch in that. And the reason I'm skipping this for now is like, I don't know if I want to draw the, you know, the 0 slope above or below the x-axis. So I'm going to skip that for a second. Now that I have this in here, though, I can see that I'm going to just need this one to be up here and need this one to be down here, unless I go with something that's not continuous, but like, do that, I don't know. I'm going to just have it be continuous and just do like that to connect through. Is everybody okay there? Mia, does that make sense as to what I'm doing? Okay. So we've done this, and this. says, g prime of 2 is negative 1, so we have that in there, right? That's basically like a negative 1 slope. And the limit as x goes to infinity is positive infinity, so this guy just goes up forever. And the limit as x goes to negative infinity is going down. So just that. That ought to do it. So it looks kind of like a cubic polynomial, right? Again, like you could have done, like where you put these points, like how high or low they go, doesn't matter. What you do after this, like you could, as long as it's pointing up at the end, you're fine. You could draw, like, you could put discontinuity in here to make it work. Like, I probably wouldn't recommend trying to do that, because that's, make things more complicated than it needs to be. For the most part, I'm going to try to make the thing continuous whenever possible. But I'm just going to kind of start putting the parts in that it's describing and then see if I can connect it all together as like a process. Does that make sense? So the part that we kind of needed was just to recognize that, like, that these are slopes. So like, I just kind of come in and do that. Those guys are slopes. I come in and do that. That's a slope. So I come in and do that. But that's the gist of it. There's no calculation I make. I'm not trying to find the equation. Ugh. No, thank you. Even though, like, now that I see what a possible answer looks like, it wouldn't be hard. Right? Your equation would just be, y equals x times x minus 2 times x minus 4. And that ought to do it, since the end behavior is for a positive odd polynomial. So that would be enough. But looking at it beforehand, I would know that. I wouldn't, even from the list of things. It'd be like, well, I can see this part, but filling in the rest is difficult. Does that feel okay?
Yeah.
Okay. You guys feel a bit better about what we're doing here? Ready to move into the next one? Okay. So this next section is still focused on the same definition of a derivative, but now we're going to be thinking about this derivative as a function instead of just calculating the derivative at a point. Here we're going to create a function that gives the value of the derivative for any x. So it's kind of like your skeleton key. Rather than keeping on doing derivative at a point, derivative at a point, derivative at a point, derivative at a point, we're just going to do it once in general for the function, and then we can plug in any values we want into our derivative function, and it'll just spit slopes at us all over the place. Does that feel okay as what we're doing? So this is the first time you've really encountered something aside from composition that's an operation on another function, right? Typically, if we talk about adding, subtracting, multiplying, dividing, these are things you do on numbers. And maybe sometimes you like multiply two functions together or something like that. That's not out of the realm of possibility, but like this is like a new operation now that operates on a function whose output is now another function. Is that okay with everybody? And so look at the change we make. Derivative at a fixed value a, the derivative function. What is the only difference between these two formulas? I'm just using an x instead of an a. Is that going to change materially any way the process works? No, man. It's just, you have an x instead of an a, and like, oh my gosh. It's the same thing, right? You see how nice that is compared to, like, oh, this is like kind of a nothing at all, right? Nothing going on. All right. So let's do kind of a conceptual example here. So here we're asked to sketch the derivative for this function f of x, and all we've been given is the graph of f of x. Everybody okay with that? So when I'm looking at the graph of f of x, what I want to be looking at is the slope. So the first thing I'm going to do is identify the places where the slope for f of x is 0. How many places do you see where the slope is 0 for f of x? Should see 3. What are the 3? The extrema. Right? Those are places where the slope of the tangent line would be 0. So the first thing I'm going to do is draw in those as my x-intercepts for the derivative. Everybody okay with that? Now I'm going to look in between. So if I look at this part of the graph, the slope is negative because it's sloping down. This part, the slope is positive because it's increasing. Negative slope, and then positive slope again. Is everybody okay with that? So if I draw this then, I'm going to have negative derivative, positive derivative, change to negative, back to positive, and then positive from there on out. And that's a decent sketch. Notice all I did was look at where the derivative was going to be 0 and whether it was going to be positive, negative in between those zeros. Is that okay, Anthony? Doesn't it come from the top? What do you? Well, this has a negative slope here, right? Like it's negative slope for the whole time, right? So it's negative slope down here, right? So when you think about the derivative, you're thinking about x, and then slope is the y-axis. So if I have x comma negative, it'll be down here, right? Did I answer it? No. Right. But the value, the y-coordinate, here is x comma slope on the derivative. So the slope here at this x value is negative. So when I plot the derivative, it should be x comma a negative value. So it should be on below the y-axis. The slope of the derivative will not be related to the slope of the function. The y-coordinate of the derivative will be related to the slope of the function. That does it? Okay, good. Again, if I don't answer it, go ahead and press me more, and make sure that we get a satisfying answer to that. Does everybody else caught what Anthony was asking about? We see what's going on here. Good question. Now, could I make this sketch more precise? I mean, they gave us some scales in here with ones and stuff. I mean, if I look at this part of the graph, that looks like the slope is about 1, right? So maybe I could plot the slope up that high, and you could, this one's a little steeper, so this one maybe is that maybe is -2, so I can put it a little lower. And you could maybe improve your sketch a little bit in terms of the heights of the humps in between our zeros. But I think that's for the most part good enough for what you'd be asked to do. On a multiple choice test, you're given the derivative and you're given 4 graphs to pick, or the function given 4 graphs to pick the derivative. That's essentially all you do. It's just identify where the zero should be, make sure the zeros are there, identify whether it should be positive or negative in between the zeros, make sure the graph is positive or negative in those places, and that should be good enough to check it. Is everybody okay? So here it asks us to find the formula for f prime of x. Switch back to black. I know people in the back, it seems like the red is hard to see. So I'll just use my definition as given before. Right. And this one's going to be long, just to let you know. It's the stupid cube in there. Well, we won't make it that long. Is everybody okay with how I got to there? See the substitution that happened? Kind of like a function composition. Make sure you can see it before I move on. I'm pausing here so you can process like a little bit what happened. We're good? If you're not, speak up. We can always, I can fill in some more blanks or like elaborate a little bit more. So I need to FOIL this out now, right? You guys remember the binomial theorem and Pascal's triangle to do this quickly in your head? Yeah, that's how I'm going to do this. I would not ask you to do like FOIL out a cubic in your head on a test or a quiz until we get the shortcuts that where you don't even need to do the foiling. So I took the x plus h, oops, and then I plug it in to f, right? So I have this guy cubed minus this guy. Happy? Perfect. So that's what I'm going to do this. Again, I would not expect you to do the same, to be able to do this in your head. I would not ask you to do something that's like this obnoxious or tedious on a test or quiz, because all it is time consuming. I made this squared. The point of the problem doesn't change at all, but it's massively faster to do by hand. So like, why would I bother? But that's what I'm about to do, is just using the binomial theorem. Oh. Thanks. So again, the coefficients for your binomial expansion are going to be like the third row of Pascal's triangle. So 1, 3, 3, 1. And then yes. Yep. So 1 was it? It's 1, 4, 6, 4, 1. I think it's the next row or something. Just add the 2 above it down. Was that right? So combining like terms, let's see, this guy and this guy, this guy and this guy. Yes, Caroline. That's okay. Everybody happy? Okay. Notice everything left has an H in it, right? So let's do some reducing. 3x squared plus 3xh plus h squared minus 1. Everybody happy? Direct substitution time. And this just, all the things with the h's drop off. There's my derivative. Feels exactly like we did last time, right? Just x's instead of a's, but like, what did he do? It's like the same thing, right? Just a different letter. Letters don't matter to us. Just a name is a name. All right. Then it asked us to compare the graphs of these two. Let's do that electronically because nobody's got time to want to do that by hand, right? Like, I'm not interested. Are you interested? No. I mean, I could like sketch it in, I guess, close enough to do it, but let's just ask the calculator here. So we're going to do x cubed minus x, and then 3x squared minus 1. And I use this calculator all over the place, so I'm just going to go and zoom standard that. So it gets it back to a normal window. So the blue is the function, the red is the derivative. Notice at the extrema, the mins and maxes. For f, the derivative is at 0, right? Those are the x-intercepts for the derivative. Where the function has a negative slope, the derivative is below the x-axis. Where the function has a positive slope, the derivative is above the x-axis. Or where the function has a positive slope, again, the derivative is above the x-axis. Everybody feel okay there? So we notice here, f was a cubic polynomial, and its derivative was a quadratic polynomial. Wonder if there's a relationship between the degree of the polynomial and its derivative. That's kind of the natural question to ask here. That's kind of the point of looking at this, was to go, I wonder so we'll circle back to that. I think that happens today. If it doesn't, it's the next section. But like, plant that in the back of your mind here, because that's where we're heading. Find the derivative of this, okay? Well, is everybody okay if I just cut through writing out the definition of the derivative again and just plug this up in and keep this thing moving? Indeterminate here, right? If we try plugging in 0 for h, what should we do? Yeah, excellent. Multiply by the conjugate, yep. Oops. Let me first do this. We happy with that? So we simplify. I notice the plus x minus x cancel each other out. And then the h reduces. So if I plug in now at that, is everybody okay if I skip the plugging in and just like write down the thing? See what I did? Pointing out when I'm skipping a step here, just nobody like, wait a minute, what did you do? I skipped a step. We're okay as long as we're okay. I'm gonna say it and just do it. Saves everybody a little bit of writing. Asks for the domain then of this derivative. So the domain of this is going to be, well, I know that because it's a square root, I can't have any negatives, right? And I know because the x is in the denominator, I can't have a zero denominator, correct? So it's going to be everything greater than 0. Is everybody okay with that? Oh, I got the domain there.
Explain that.
Sure. So, because I have square root of x, that tells me that I have to take the non-negatives. Because I have a 1 over x, tells me x cannot be 0. So this just turns it. Does that make sense? Helps. Sure. So the way that you want to look at that is you want to think about your operations and what operations can cause an undefined result. So addition and subtraction, nothing can give you an undefined problem. Multiplication, nothing can give you an undefined problem. Even roots can't do negatives. Fractions or division can't have a 0 denominator. So that's what I see here. So what I'll do is I'll take the stuff under the radical and like I'll set that has to be greater than or equal to 0, right? And then I'll take the stuff in the denominator of the fraction and say, okay, well that cannot equal 0. So if I solve for x, I just get x cannot be 0. So if I draw this then like on a number line, I have greater than or equal to 0. I have not equal to 0. If I take the intersection of these two sets, that's going to be like that part, right? Which is, does that feel better in terms of like a systematic approach to it? And that's really kind of the best you can do. It's just like what operations can give me undefined. Let's take each of those operations and look at them individually, and we'll take all their relative domains and take the intersection of them. And that'll give you the domain for the whole thing. Okay. So the domain for f prime was x greater than 0, right? But what was the domain for f? Right? What do you notice? They're different. They differ by exactly one number, but they're different. So apparently at 0, the derivative fails to exist. Tuck that away, but that's an idea we're going to circle back to about when a derivative fails to exist and the relationship between the domain of a function and the domain of its derivative. Will we be able to predict where the derivative will fail to exist based on what we know about the function? Yes, will be the answer to that, and we'll get to it. Okay, I'm just kind of planting some seeds that we'll be harvesting in the next coming sections. Everybody still good? All right. You guys want to try this one here in your notes, and we'll go through it here in a second. Once you guys do that, it's good practice. This one gets kind of yucky, so I think it's a good one. Like the algebra just gets messy. But if you're a symbol pusher, you're like, this is what I've been waiting for. Let's get our algebra going here. Yes. Get away from this conceptual mumbo jumbo we've been doing. Like, push me some symbols. And I'll just periodically go down and write down some intermediate steps as we go. So if you're working and you see like, ooh, I messed up a negative, like you can see it and fix it and stuff. So I'll just kind of here and there write in some more steps. Sound good? That's probably the trickiest step.
Why is it on minus? On top of that
Right? Like punishingly detailed on the negatives, but like easy to mess that up too. Like easy place to make a mistake. You'd know when you got to the, I guess in this case it would be harder to see it at the end because the H would still be the only thing left, but it's not the right sign, so that's a little tricky. And this is like kind of as bad as your algebra is going to get out of one of these problems before we start putting the shortcuts in. Did I mention this already? That there's like, that these are all problems that we're going to abandon our limit definition here fairly quickly and just look at like the shortcut way to go through these, because the limit definition is kind of a bear. You know, like it's a lot of algebra, a lot of writing, kind of inefficient. A lot of these problems from school I can look at and do in his head with the shortcuts, but no way I can like do it with the limit through my head. And that's the goal for you guys as well. Like a lot of these simpler functions, to be able to look at and just be able to write down the derivative or the derivative of the function like almost instantaneously. which is great, right? Like, think about how much of a hassle this is to step through all this work. Now, don't get me wrong, there's still going to be stuff on occasion, especially in like a multiple choice type setting where there's like nothing you can do other than use the definition of derivative. Like, that's not going to go away completely, but like, we're going to minimize it as much as we can in favor of easier and more efficient methods. Is everybody happy with what we got to down here? Is that helpful to just like have a minute to kind of work through stuff and get some feedback as you go and try to keep up with what we're doing? So here's a bunch of different notations that all mean the same thing. We're talking about the derivative of the function, whether it's f prime of x, or y prime, or dy dx, or if it was f, it would be df dx, or d dx of f of x, or d of f of x, or dx f of x. These two are rare. You almost never see those. The rest of these are pretty common, but they're all meaning the same thing. So remember, what is a derivative essentially? It's essentially like a slope. So remember, your slope formula could have been written as like change in y over change in x with the Greek letter delta. That's that notation essentially. Instead of the delta, we have a d, because instead of doing an average rate of change, we're doing an instantaneous rate of change. So we just tweak the notation just a little bit, but that should remind you of that. In this notation, we've written kind of the d dx as like a derivative operator, like that's like an operation on the function f of x. So if you're showing work and you want to take like the derivative of both sides of an equation, which would be something we'll do later in the point, like that's a good notation to use, like d dx to both sides, or whatever the variable in question is, t or an s or y or whatever. All right, so let's start talking about differentiability. So this is a new definition. So we say a function f is differentiable at a if f prime of a exists. So if I can find the derivative at a, then the function is differentiable at a. Okay? We say f is differentiable on an open interval from a to b if it is differentiable at every number in the interval. Yes, Steve. So the derivative exists. We can find the derivative at that value. So if it's differentiable over the interval, every x on that interval we can plug in and find the value for the derivative. So let's take a look at the absolute value of x. This is kind of your canonical example here. That's what the graph of the absolute value of x is, right? What's the slope of the function on this interval here? Just use your eyes. Well, -1, right? Because it's going down. Yeah. But Good. And what's the slope of the function on this interval? Positive 1. What's the slope there? Well, let's think about this. So f of x is equal to the absolute value of x, right? So that means we're negative x when x is less than 0, and it's positive x when x is greater than 0, right? That's our piecewise definition. So if I look at the limit as x approaches h from the left, I know I need to use a left and right hand limit because it's a piecewise function. So I would have f of x plus h minus f of x over h. So I'd have negative x minus h minus negative x all over h. Oops, got my limit. If I look at that, boom, boom, and it just simplifies down to negative 1, right? We do the same thing from the right. Get 1 for that slope. Since these two limits disagree, what would we say? Does not exist. So, the takeaway, you see how the slope changes here abruptly, where it's going from negative 1, negative 1, negative 1, positive 1, positive 1, positive 1. At that abrupt change in slope, the derivative is going to fail to exist. As opposed,
Good morning, Notre Dame Prep. Please excuse this announcement for a quick drill. At this time, we are going to do a lockdown drill.
Okay, so this previous example. Oh, what now? Okay. So what is our conclusion? We'd say that it is differentiable from negative infinity to 0, and 0 to positive infinity, but it's not differentiable at x equals 0. And again, we did this part, we did rather informally, right? That was just, we looked at the graph and went, well, the slope there is always this, and the slope there is always that. Now you could do that, to do that rigorously, would you do the limit as x approaches, or as the limit as h approaches 0 of f of a plus h minus f of a over h, and you just say, well, for h between, or for a between, negative infinity and negative 1, that is, just negative 1. It's going to simplify down to a. And then you say, okay, for a in 0 to positive infinity, that just simplifies down to a, to 1 also. That's all that's the difference, but that's easy enough to do. All right. Tremendously important theorem. If f is differentiable at a, then it is continuous at a. differentiability implies continuity. Is the reverse true? No. What's your counterexample? This, right? Continuous everywhere, but not differentiable at 0, right? Continuity doesn't give you differentiability, but the reverse is true. Differentiability guarantees continuity. Okay? You'll use that fact over and over again. So it's one that you want to make sure that you got, and you know the correct direction. It's not if and only if. One doesn't imply the other forward and backwards. It's only differentiability giving you continuity, not the reverse. So let's look at places where the derivative fails to exist. There are 3 canonical examples. Okay? A corner, where the slope changes abruptly from positive to negative, typically. But even if it's like, or something like that, where it's still positive slope, but it's abrupt, that's going to be enough. A discontinuity. And then the third is a vertical tangent. So like, again, so like your canonical examples of these things, like absolute value, cube root, and then this is just like kind of potentially any piecewise. But it's easy to make a corner with a piecewise function too. You guys okay with that? We can take the derivative of a derivative, call that the second derivative. So it'll tell you the slope of the tangent lines to the slope function of a function. And you're like, what good is that going to do? Well, it turns out that graphically the second derivative has implications about the concavity of a function. Whether it's like concave up, where it forms like a cup, or concave down, where it forms like a dome. We'll explore that more later. So here it asks us to do f double prime, that's the second derivative. So we did the first derivative already earlier in the lesson, right? So I'm going to take advantage of that so I don't have to do like that over again. That was kind of a lot of work to get to that point. No, there's no good way to go straight to the second derivative. But the process of doing a derivative is going to get a lot easier in like 1 or 2 more sections. I think the next section we start getting into the shortcuts. All right, so the second derivative then. Hi, Kylie. Is that, right? Notice now the primes are supposed to be there because we're actually taking the derivative of a derivative. Everybody's good? Just doing things the same way. Nothing has really changed. Okay. I'm just going to multiply this stuff out up above. And then So left with limit as h goes to 0 of 6x plus 3h, or just 6. So again, notice what's happened here. We've gone from a cubic as our f, a quadratic as our f prime, and now a linear as our f double prime. Right? So again, it looks like, at least for polynomials, this process of taking the derivative, we're going to lose a degree off of our polynomial each time we do that. Does that feel okay to everybody? Okay. Important physics note, because you'll get some story problems that involve acceleration, velocity, and position. So acceleration is just the first derivative of velocity, or you can think about it as the second derivative of position. It means velocity is the first derivative of position. Everybody's okay with that? So again, there's nothing really more to say there, just like if you're involved in a story problem situation and you're given a velocity and you have to find the acceleration, what do you need to do? Just take the derivative. Everybody's good? Okay. We can do third derivatives. Oh dear, Mr. Kulik. So notice this is still that same function we've been working through. So let's do that. What do you notice that's happening each time I take one of these derivatives, though? Yeah, and the process is getting simpler, right? It's getting easier to do this. Like the algebra headache is getting much less. I want to do the fourth derivative then. Well, if you think about it, if the slope of this is, or if this function is just 6, that's a horizontal line, right? The slope of a horizontal line should be 0 everywhere, right? So f of x plus a, there's no x. It's just 6 minus 6, so it's just like 0 over h, which is just, that's going to wrap us up here for this section today. Did this feel okay? This should have felt like a natural extension of what we did last time. If you were a little befuddled last time or turned around, getting it kind of the second time through here today should have, I think, really helped clear things up and like, okay, it's just like the same process over and over and over again. When we get into chapter 3, the first order of business is going to be, how do I get away from having to do this limit business all the time? Like, let's start looking at some shortcuts here. All of chapter 3 is like building out shortcuts. So we're going to do 3.1 and 3.2, and then we'll be ready for our next test. So again, like I don't want to stack too much stuff before test time. And then after test 2, we'll have the rest of our derivative rules and get into a little bit of start some application test and then to finish the application of the exam time is typically how that would work.
When you learn the shortcuts, do you have to do the long way on the test?
Never again. unless you absolutely have to do it, you know, like, you don't
When you
have.
ask us, like, do not use this shortcut.
Well, I haven't written the test yet. I would imagine there'd be no more than one question where I ask you to use the limit of a derivative, or the limit definition of a derivative to evaluate this derivative. But more commonly, the way that we would do this is like, so Marcelino, more commonly, the way we do this is we give you something like this on the test, and the hope is that you recognize this is the derivative definition, the limit definition of a derivative, and do the derivative by hand, not have to go through the limit. So you recognize it as, oh, that just means the derivative of x cubed plus x plus 1. I'll just do that with the shortcuts and answer this limit question. That's the more common presentation where you need the limit definition so that you recognize how to do that without having to mess around with all the limit stuff. But yeah, good questions.